In Unit 3, we've been talking about quadratics a lot. We've been factoring them, we've been looking at what their graphs look like, identifying their key characteristics like their vertex and the axis of symmetry. All of these quadratics have been pretty generic. They didn't have much meaning, kind of like an analogy that I was thinking about. Picture a Mercy Macaulay wolf. What does she look like? Well, if I just leave it at Mercy Macaulay Wolf, that could be any student. Obviously, you'd be picturing a female, probably gray skirt, orange polo, white polo, but it doesn't look very specific until we put a name with the Mercy Macaulay Wolf. If I were to name a Mercy Macaulay Wolf specifically, you would imagine the shape of her face, how tall she is, does she wear glasses, does she wear her hair in a ponytail? You would have much more specific information to describe that Mercy Macaulay wolf. And that's what's going to happen with our quadratic. Instead of just seeing the generic parent function, f of x equals x squared, that could be any quadratic, that's very generic. We're going to look at what happens when we put different numbers around the parent function. What happens when we put a number before the x squared? What happens when we add or subtract a number after the x squared? What happens if we add or subtract a number with x before we square it? All of these things are going to have impacts on our parent function, and it's going to change the look of that generic parent function so that it's a very specific looking quadratic. So let's start by going into Desmos. If you click on Start Graphing, I believe. Yes, you'll click on Start Graphing. And then if you go over to these little pancakes up here at the top and click on them, a bunch of options open up. Please click on the one that says Parabola's Vertex Form Example, because all of the ones we're looking at will be in vertex form. And open up the graph. As you can see, we have a variable before the x squared. We have a variable inside with x before we square it, and we have a third variable k outside the squaring that happens at the end, added or subtracted at the end. And we're going to see what that does to our generic parent function. So to start, let's start with a. What happens as a gets bigger and bigger and bigger? So it starts off at 1, and as it gets bigger and bigger and bigger, do you see how the graph is narrowing? It's getting skinnier. That's called a dilation. What happens if a gets smaller? Well, as it gets a little bit smaller, like a fraction, see how it gets very wide? Until it gets down to 0, then it's completely flat, which isn't very interesting. In fact, that's not a quadratic anymore, that's a line. But as it gets negative, it flips. And now it gets skinnier and skinnier and skinnier, facing downward. So when a is negative, our quadratic opens down. When a is positive, it opens up. And the bigger the number a, the skinnier it gets. And when it's a fraction, it gets flatter, called a compression. Let's get back to a equals 1. We'll leave it at that. So we can just look at h next. What happens as I move h up, as h gets bigger? As h gets bigger, it's moving to the right. As h gets smaller, it's moving to the left. All right, put that back at 0. How about k? What do you think k is going to do? Well, if h moves it left and right, k moves the graph up or down. When k is positive, it moves it up. When k is negative, it moves the graph down. So now you've kind of had a chance to play with these numbers. Take a moment, if you haven't played around with them on your screen, and move some of these numbers. See what happens to your graph. Going back to our notes now, That's why I had this screen grab right here at the start to tell you to go into Desmos and practice what happens. By the way, vertex form, this is just a form of a quadratic. It's not the only form. There's also standard form. We've dealt with both. But when we're trying to just look at the quadratic and see what's happening to the quadratic, we want it to be in vertex form, kind of like when we were graphing lines a few steps ago. It's much easier to graph a line in slope-intercept form than when it was in point-slope form or standard form. We like being able to just look at it and easily see the slope and easily see the intercept. And that's what this form allows us to do with a quadratic. We can easily see the vertex and we can easily see the dilation factor before it. So let's take a look at a few examples. -3 times the quantity x minus 2 squared minus 4. Well, the vertex is the h and the k as an ordered pair. So in this problem, h, the number that's subtracted from x, is a +2. That's the most confusing part. The easiest way to think about this is to look at what you have here. Look at the number next to x in the parentheses. To get the h value, you're going to put the opposite sign of h. The k value is going to be the entire number that's added or subtracted after the squared parentheses. So sometimes k will be positive, sometimes k will be negative. You keep the sign with the number. So notice we just looked at these numbers in vertex form. We saw -2, -4. So we immediately knew that the vertex was 2, -4. Change the one in parentheses and keep the one outside the parentheses. Let's fill in the vertex for the next 4 examples. All right, for the next one, the opposite of 2 is -2. The number outside is just 1. Opposite of -1 is +1. The number outside at the end is 5. My vertex is 1, 5. The opposite of -6 is 6. The number outside is -7. And finally, the opposite of -2 is +2. The number outside is 1. Now, we need to decide if these are going to be max values or min values, maximums or minimums. One way is to type the entire thing into Desmos and look at a picture. You'll be able to tell right away if it opens up or down, and if this point is at the very tippy top of the curve or at the very bottom of the curve. However, there's a faster way. We can just look at the a value. If a is negative, remember that made it open down, which makes this vertex point a maximum. And the next one, it's invisible, but a is 1, which means it's positive. It's going to open up. And this vertex will be a minimum. In the next one, a is negative, which means it opens down, which makes this a maximum. A is +1 in our 4th example, which means it opens up, making the vertex a minimum. And finally, a is a -1/2. Negative means it opens down, which makes this a maximum. Let's talk about the shift. If you recall, when we adjusted the h value, it shifted the graph left and right. So I'm going to look right here at this number, now that I have the vertex. It's negative, so it's going left 2. But if I didn't have this column to look at, if I was looking straight at my equation to start with, it's going to go the opposite of what you'd think, because remember, it's in parentheses, so we're taking the opposite of what's natural and intuitive. Notice the next one. The opposite would tell me go right 1. It matches the vertex, positive 1, right 1. But that's probably the easiest part about this process, about this step. That's the most tricky part, is the h value. Finally, we have right 6 and a shift right 2. The k value is very intuitive. If k is positive, it goes up. If k is negative, it goes down. So if we just look at these k values, up 1, up 5, down 7, up 1. You're just literally reading the number. You don't have to think that it's the opposite or anything. If it's positive, it goes up. If it's negative, it goes down. So what this literally means is if we start off with our parent function and apply these translations, we will move our parent function around the graph. The first one will go left 2 and up 1. Instead of being right here, if I went left 2 spaces and up 1, it would now be up here. I also know from looking at the first one that it would reflect. It would be opening down, and it would be a little more narrow because of that 3 value, which brings me to my next chart. Some of these examples are very similar to the ones we just looked at. Let's talk about if it opens up or down, and if there's been a reflection. So, has this been reflected? If it's negative, it's been reflected over x, so we would say yes. That means it opens down. This is positive 1/2. So there's no reflection, it opens up. This is negative. That means it's been reflected. Yes, it's been reflected, and it opens down. This is positive 1/5. No reflection, it opens up, just like the parent function. The parent function opens up. This last one is negative, so yes, there was a reflection, and it opens down. Let's take a look at the dilation factor. When A is bigger than 1, it's going to get skinnier. Here, A is 3. I should say the absolute value of A. Absolute value of A greater than 1 is a dilation. So we're no longer looking at the negative sign. This is one of those rare times that Mrs. Merck says split them apart. We're just looking at the number. We're taking the absolute value of it. That's an easier way to think about it. 3 is bigger than 1, so it's a dilation. 1/2. That is not bigger than 1. Here we would say A is less than 1, so it's a compression. If our original function had this shape, our new function is going to be flatter, as if something were compressing it down and smushing it. The next one, the absolute value of A is bigger than 1. 23 is bigger than 1. A is bigger than 1, so it's a dilation. Here, A is a fraction again. And not just a fraction, but a fraction that's less than 1. A is less than 1, so it's a compression. We must be very careful not to just see a fraction and assume that it's compression, because if this was 6/5, 6/5 is bigger than 1, so that would be a dilation. The next one is a -1. The absolute value of that is 1. No change. It has not gotten skinnier or wider. It's not been dilated or compressed, neither. The axis of symmetry is simply going to be our x value. So if we go back up to our vertex, all of these first coordinates will be our axis of symmetry. X equals 2, x equals -2, x equals 1, x equals 6, x equals 2. For the first example, again, it's the opposite because it's the h value. So x equals 2. And the second one, when we take the opposite of the number in the parentheses, it's -2. Opposite of -1, axis of symmetry, x equals 1. Opposite of -6, x equals 6. And finally, the opposite of -2, x equals 2. Now we need to talk about the range. This is probably the most challenging part to do without looking at the graph. It's easy to be done. It can be done. But when you're starting out, I want you to start out by looking at it on your graph. So we're going to take -3 times the quantity x minus 2 squared minus 4, and we're going to put that into Desmos. So I'm going to close out on my vertex form, new blank graph. That's what I want. I'm going to say y equals -3 times parentheses x minus 2, x minus 2. Let me just double check that I'm doing the right one. Yes, the quantity squared. And then we also had -4. -4. So if I look at this graph, here it is. I'm going to zoom out so you can see a lot of it. Notice that the vertex has been shifted. Whoop, come on back to me here. The vertex has been shifted right 2, down 4. Notice that it flipped over the axis. It was reflected. It's opening down, and it got skinnier from my parent function. I should probably put my parent function on there so you can see what we started with. Y equals x squared. This is what we started with. It's reflected. It's moved down. Now we need to talk about the range. You can think of the range as like a window shade that can go up and down. For our red graph here, I'm going to turn off my blue graph for just a moment because I don't want to look at it right now. I want to know how I could pull the shade to cover this. Well, it starts at the bottom here. So some windows have shades where you can just pull them up. That way you can still have a little bit of sunlight coming in, but you have privacy. So we could pull a shade up from the bottom, and we would pull this shade all the way up. Imagine taking a line and pulling it up until we get to here. So think of it as climbing this thermometer. From -infinity, we're going up, 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 getting bigger and bigger and bigger until we get to -4. Let me zoom in so you can see that. So I'm starting at -infinity. I'm going up all the way until I get to -4. That's why we say that from -infinity all the way up to -4 is the range. That's the only place where you will find this graph living, is between -infinity and -4. If you go higher than -4, you won't be on the graph anymore. Like -1. I can't move left to right here and touch my graph anymore. I'm too high. I'm out of the range. So let's try the next one. Let's look at a picture again. The next one is half x plus 2, the quantity squared, plus 4. Y equals half x plus 2, the quantity squared, plus 4. Zoom out so we can find it. Oh, there it is, our green graph. Notice if I turn my original function on, it's moved left 2, up 4. It's a little bit wider than it used to be because of this compression factor of 1/2. And now I can think about my window shade. Notice it's at the top now because it's opening up. If I pull a window shade down to cover up this graph, I would start at the top. The top is infinity, and I'd pull it down until I get to 4. Now, we don't want to put positive infinity to 4 because if you think about a number line, 4 would be here. Positive infinity is on the right of 4. So we want to write it in that order, from left to right on a number line. So we would say it goes from 4 to positive infinity. Next one, negative 23, x minus 1 squared plus 4. Negative 23, x minus 1 plus 4. And there it is. I'm going to turn that one off, turn my parent function back on. Notice it got much skinnier because 23 is a very big number. And it is opening down because it's negative. It's also moved right 1 and up 4 for that vertex. So again, I would start my shade from the bottom, negative infinity. I could pull it up, 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 up until I get to 4. That's kind of a coincidence that these are all ending in 4, but I think that's just a coincidence based on the examples we've chosen. Finally, this will be the last one we do. I'll trust that you can do the last one without the graph. 1/5 x minus 6 minus 7. Y equals 1/5 x minus 6 minus 7. Oops, squared minus 7. There it is. It's wider than the parent function. It has moved right 6 and down 7. And we would start our shade at the top, and we would close the shade, moving it down, 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 until we get to negative 7. So from positive infinity down to negative 7. But remember, positive infinity likes to live on the right, and negative 7 would be on the left. Positive numbers are on the right, negatives are on the left. So that would be our answer. Notice the pattern here. Our range went up to negative 4, from 4 to infinity, from negative infinity to 4, negative 7. So we know this next one's going to have a 1, but what we don't know without looking at the graph at this point, is it negative infinity to 1, or is it 1 to infinity? Well, remember, we can tell if this graph opens up or down. This one opened down, so it went from negative infinity to the number. This one opened up, 4 to infinity, 4 up. This one opened down, negative infinity to 4. This one opened up, the number to positive infinity. This one opens down, so it's going to go from negative infinity all the way up to 1. So that's my answer without graphing it. It is possible to do them without going over to Desmos and typing it in, but using Desmos is a very easy way to check and to look at things visually instead of having to consider how K and A relate together to make the range.